Hey everyone, ready for a deep dive into something really cool?
I know I am.
Today we're tackling reinforcement learning.
Oh, wow. Yeah.
The kind of AI that's not just, driving those self-driving cars
Right.
or,
Yeah.
powering game-playing champions.
Mhm.
It's got the potential to completely change how we approach things like personalized education.
Yeah. What's so cool about reinforcement learning is that it really mirrors how we learn in real life,
Yeah,
interacting with the world, making decisions,
definitely.
and learning from the outcomes.
Mm-hmm.
You do something good, you get a reward, you make a mistake,
Right.
there's a penalty,
Yeah.
just like in the real world.
I like that learning by trial and error. you
Yeah.
know, Figuring things out as we go.
Mm-hmm.
So to really unpack this,
Okay.
we're going to be looking at some lectures from Stanford's CS234 course on reinforcement learning,
Great.
taught by Emma Brunskill.
Awesome.
And one thing that jumped out at me right away was how this goes way beyond just games and robots.
Absolutely. Brunskill's lab is actually using these techniques to try and revolutionize healthcare and education.
Whoa.
Imagine AI creating a personalized learning plan that adapts to your strengths and weaknesses.
Oh, wow.
As you go, it's like having a super tutor
Yeah.
powered by AI.
Now that's a game changer.
Right.
But before we get too far ahead of ourselves, let's kind of break down these core elements of reinforcement learning.
Sure.
What are those key pillars that make this whole thing work?
Okay, so at its core, reinforcement learning is about four things:
Okay.
optimization,
Mm-hmm.
delayed consequences,
Okay.
exploration,
Got it.
and generalization.
Okay, so let's start with that first one, optimization.
So optimization is all about figuring out what actions
Yeah.
will lead to the biggest rewards.
Okay.
Kind of like strategizing to win a game.
Okay, that makes sense.
Yeah.
So what about those delayed consequences?
Okay, yeah.
Is that where things get a bit more complex?
Exactly. Delayed consequences highlight that sometimes.
Mhm.
The impact of our actions isn't immediately obvious.
Right.
It's like making a strategic move in chess.
Yeah. Yeah.
You might not see the benefits until several moves later.
Ah, so it's about thinking ahead.
Yes.
Understanding that the best action now
Mm-hmm.
might not be the one with the most immediate payoff.
Exactly.
But how does this set reinforcement learning apart from other AI approaches?
Okay.
Like I know we've got things like planning,
Right.
supervised learning,
Yeah.
unsupervised learning. Where do they kind of fit into this?
Good question. Think of planning, like designing the perfect chess moves based purely on the rules of the game.
Uh-huh.
No learning from experience needed.
Right.
It's powerful, but limited
Gotcha.
to situations where we already have a clear model
Okay.
of how things work.
So planning is like having the instruction manual,
Yeah,
while reinforcement learning is more about figuring things out on your own.
exactly. Now, supervised learning is like teaching an AI to spot faces in photos.
Okay.
We feed it tons of labeled examples,
Yeah.
telling it, this is a face, this isn't.
Right.
No need for trial and error.
And what about unsupervised learning?
Yeah.
Is that similar?
It is, in that there's no direct feedback or reward involved.
Okay.
Unsupervised learning is more about finding patterns in data.
Right.
Without explicit labels, think of it like an AI clustering customer data into different groups
Gotcha.
based on similarities it discovers.
Interesting. So with all these different approaches,
Yeah.
what makes reinforcement learning stand out? What's its unique strength?
It's the way it tackles those delayed consequences that's what makes it so powerful.
Okay.
For things like self-driving cars,
Mm-hmm.
a car can't just focus on staying in the lane.
Yeah.
It needs to make decisions that will eventually lead to reaching the destination safely,
Right.
all while navigating
Yeah.
a constantly changing environment.
That makes a lot of sense. But I'm curious about something Brunskill brought up in her lectures.
Yeah.
Where do these rewards actually come from?
Oh, that's interesting.
In reinforcement learning, who decides?
Yeah.
What's good and bad for the AI?
That's where the art and challenge of reward design comes in.
Okay.
If the rewards are designed poorly, the AI can learn the wrong behaviors.
Oh, no.
Imagine teaching addition and subtraction to an AI,
Yeah.
but the reward system is messed up. It
Yeah.
might end up giving students problems that are way too easy or too hard,
Right.
completely hindering their learning.
Okay. That's a really valid example.
Right.
It makes me wonder about the complexity of real-world applications.
Yeah.
Think about something like an Atari game.
Uh-huh.
The AI has to learn from just pixels on a screen,
It's true.
figuring out what to do
Right.
in this incredibly complex and ever-changing space.
Yeah.
How can it possibly make sense of all that data?
That's where a technique called function approximation comes in. We use tools like deep neural networks
Yeah.
to help the AI represent complex relationships
Okay.
between its actions and the consequences,
Hmm.
even in incredibly challenging environments like video games.
Wow.
It's like giving the AI a powerful set of tools
Yeah.
to understand and navigate its world.
Fascinating. Brunskill also mentions this method called Monte Carlo tree search, or MCTS.
Oh, yeah.
It's almost like the AI is thinking through every possible scenario
Yes.
before making a move.
That's a great way to put it. MCTS allows the AI to simulate millions of possible futures,
Oh, wow.
helping it explore a vast range of possibilities and come up with strategies
Yeah.
that even surprise us humans.
It's almost like the AI is playing out a game of chess in its head,
Mm-hmm.
considering every possible move and countermove
Yeah.
before making its decision.
Right.
That's incredible.
It is.
And it makes me think, what if we could apply this kind of strategic thinking
Yeah.
to our own decision-making?
That's a great thought.
What if we could simulate different outcomes
Yeah.
before making a choice?
I know it's pretty wild, but before we kind of get too deep into the potential applications, let's make sure we're all clear on exactly what reinforcement learning is.
You're right. Sometimes we get so caught up in the cool stuff that we forget to define the basics.
Exactly.
So let's take a step back.
Yeah.
What exactly is reinforcement learning?
At its heart, reinforcement learning is a type of machine learning
Okay.
where an agent learns to make decisions by interacting with its environment.
Mm-hmm.
The agent receives rewards for good actions and penalties for bad ones.
Right.
And its goal is to figure out a strategy
Yeah.
that maximizes its overall rewards over time.
So it's not just about making the right decision right now. It's about figuring out the best long-term strategy.
Precisely. And this sets it apart from other types of machine learning,
Okay.
like supervised learning, where the agent is given the right answer for every situation.
Right.
In reinforcement learning, the agent has to discover.
Best actions through trial and error.
I see. So it's not just about following a set of rules. It's about learning how to play the game and win based on experience.
Exactly. And what makes it even more fascinating is that this learning process often involves exploring new actions,
Right.
even if they lead to mistakes.
Interesting.
It's about finding the balance between sticking with what seems to work and venturing into the unknown
Right.
to discover even better strategies.
So it's like a constant process of learning and adapting,
Yes,
always searching for that best way to achieve a goal.
that's a great way to describe it. And what's really cool is that this approach has led to AI systems
Yeah.
that can do things we never thought possible
Right.
just a few years ago.
Yeah. It sounds like there's a lot to unpack here.
Definitely.
We've kind of touched on some of the basics.
Yeah,
And even glimpsed the exciting potential of reinforcement learning.
absolutely.
But I'm ready to dive deeper. Me too. Let's explore the different algorithms that make this learning possible.
Okay,
Starting with one of the most fundamental cue learning.
let's do it. Welcome back. So we've laid the groundwork,
Yeah.
exploring those core elements of reinforcement learning.
Mm-hmm.
We've even touched on its fascinating history.
Right.
But now I'm ready to roll up my sleeves and delve into those algorithms
All right.
and make all this learning possible.
Let's do it.
Where do we start?
Well, let's jump right into one of the most fundamental algorithms, cue learning.
Okay.
It's a value-based method that's been incredibly successful. Think game-playing AI,
Yeah.
even robotics.
Cue learning, the name rings a bell.
Uh-huh.
It's about figuring out the,
Yeah.
quality of different actions, right?
Exactly.
Like if the AI is playing a game,
Mm-hmm.
it's trying to learn which moves lead to the best outcomes.
It's all about learning an action value function,
Okay.
which is often represented in the cue.
Right.
This function essentially tries to predict the total reward
Mhm.
an agent will get by taking a particular action in a particular situation.
So the cue value is like a score for each possible move,
Yeah.
telling the AI how good that move is likely
Mm-hmm.
to be.
That's a great way to think about it. And based on these cue values,
Yeah.
the agent can then make decisions
Mhm.
by simply choosing the action
Right.
with the highest score in each situation.
Makes sense.
Of course, the agent doesn't know these true cue values right from the start. It has to learn them through experience.
So how does it actually learn these values?
Okay.
Is it simply remembering all the rewards
Mm-hmm.
it's gotten for different actions in the past?
It's a bit more sophisticated
Okay.
than just keeping a simple record.
Yeah.
Q-learning uses an iterative process, meaning it's constantly updating
Right.
its estimates of those Q values
Mm-hmm.
based on new experiences.
Right.
Think of it like refining a recipe. You start with a basic idea
Okay.
and keep tweaking it as you get feedback on the taste.
I like that analogy.
Good.
So how does this refining process actually work?
Well,
What's guiding these adjustments
yeah.
to the Q values?
There's a famous equation at the heart of this learning process
Mm-hmm.
called the Bellman equation.
The Bellman equation.
It sounds intimidating,
Yeah.
but it's actually a pretty intuitive idea.
Okay. All right. Lay it on me. What's the Bellman equation all about?
Imagine you're on a treasure hunt
Okay.
and you have a map with clues
Mm-hmm.
leading to the treasure.
Okay.
The Bellman equation is like that map
Right.
telling you that the value of your current location depends on two things.
Okay.
The immediate reward
Yeah.
you get for being there
Mm-hmm.
and the potential rewards you can get
Right.
by following the best path from there.
So it's not just about the immediate reward.
Right.
It's about looking ahead and considering the long-term consequences.
Exactly. And this equation
Yeah.
helps the agent connect its present actions to potential future rewards.
Right.
Even if those rewards are many steps away.
That's clever.
Yeah.
But earlier we talked about how reinforcement learning often deals with situations where we don't have a perfect model of the environment.
Yeah.
It's like exploring a new city without a map.
Right.
How can we apply this equation if we don't know exactly how the environment works?
That's what makes Q-learning
Okay.
a model-free algorithm.
Mm-hmm.
It doesn't need a complete set of instructions
Yeah.
or a perfect understanding of the environment's rules.
Okay.
Instead, it relies on trial and error learning directly from its interactions with the environment
Right.
and updating its beliefs based on what actually happened,
Right.
not just what it thinks might happen.
So it's like learning from experience, adapting its strategy as it goes,
Exactly.
rather than relying on a pre-programmed plan.
And this adaptability is one of the key strengths of Q-learning, making it suitable for a wide range of problems.
Okay.
Where the rules might be unclear or constantly changing.
This is all starting to click.
Good.
But I have one more question.
Okay.
If the agent is just starting out, it has no experience to draw on,
Right.
how does it even begin to make decisions?
Okay.
Does it just pick actions randomly?
And that's where exploration comes in.
Right.
In the beginning, the agent might indeed choose actions randomly just to see what happens.
Yeah.
Remember, exploration is about gathering information.
Right.
Even if it means making some mistakes
Gotcha.
along the way.
Okay.
As the agent gains more experience, it can start to rely more on its learned Q values
Okay.
to make informed decisions.
So it's a balance between exploration, trying new things,
Yeah,
and exploitation, using what it's already learned
exactly.
to maximize its rewards.
That's the key to success in reinforcement learning.
Gotcha.
We need the agent to explore enough to discover those hidden gems, the actions that lead to the best outcomes,
Yeah.
but also to exploit its knowledge
Right.
and make smart choices
Right.
based on what it's already figured out.
It's like trying to find the best restaurant in a new city.
Right.
You might start by exploring randomly,
Yeah.
but as you gather recommendations and try different places,
Exactly.
you'll start to make more informed choices.
And just like with finding that perfect restaurant,
Yeah.
there are different strategies for balancing exploration and exploitation.
Okay.
In Q learning, one common approach is called epsilon greedy exploration,
Epsilon greedy.
where the agent randomly chooses actions sometimes just to keep things interesting
Okay.
and ensure it doesn't miss out on hidden opportunities.
So we're injecting a bit of randomness
Yeah,
into the agent's behavior
exactly.
just to keep it on its toes.
Right.
Prevent it from getting stuck in a rut.
That's a great way to put it. And
Yeah.
as the agent gains experience, it can gradually reduce this randomness
Okay.
and rely more on its learned Q values
Right.
to make more informed decisions.
Okay, so we've got this agent exploring its environment, using Q learning to constantly refine.
Yeah.
It's understanding of which actions are best
Right.
and striking that delicate balance between exploration and exploitation.
Exactly.
This Q learning is pretty impressive.
It is, and it's been a cornerstone of reinforcement learning.
Yeah.
Powering a wide range of applications from those game-playing AIs we talked about to robots
Right.
that can learn to navigate complex environments.
This is all so fascinating.
It is.
But we've been focusing on Q learning and those value-based methods.
Yeah.
You mentioned earlier that there's another side to this reinforcement learning coin.
Right.
What are those policy gradient methods all about?
You're ready to dive into a whole new perspective.
All right, let's do it.
Unlike value-based methods that focus on figuring out how good each action is.
Right. Policy gradient methods
Yeah.
take a more direct approach.
Okay.
They try to directly learn the best strategy for choosing actions without needing to explicitly estimate those Q values.
So instead of learning the value of each move,
Yeah.
it's learning the optimal strategy.
Exactly.
Like a master chess player.
Right.
Who intuitively knows the best move in any situation.
That's a great analogy. Imagine learning to ride a bike.
Okay.
Instead of trying to calculate the precise angle to lean or the force to apply to the pedals,
Right.
you're developing a feel for it.
Yeah.
Directly learning the actions
Okay.
that keep you balanced and moving forward.
I like that it sounds more intuitive, more like how we learn in the real world.
Exactly.
But how does the AI actually learn this strategy without relying on those Q value estimations?
Okay.
What's guiding its learning process?
Policy gradient methods work by searching for the best set of parameters.
That define the agent's policy.
Right.
It's strategy for choosing actions.
Gotcha.
It's like fine-tuning. A complex machine constantly adjusting the knobs and levers to achieve the best performance.
So we're not calculating Q values anymore.
Right.
But we're still trying to optimize the agent's behavior.
Exactly.
To get the most reward, it's like climbing a mountain.
Yes.
Constantly adjusting our path to reach the highest peak.
Exactly.
Where the reward is greatest.
You're exactly right.
Okay.
The mountain here is the reward landscape.
Right.
And those policy parameters are like our guide, leading us to that peak reward.
Got it.
But just like navigating a real mountain,
Yeah.
there are challenges.
I can imagine. What are some of the obstacles these policy gradient methods have to overcome?
One major challenge is the noise inherent in reinforcement learning environments.
Noise. Okay.
Think about a robot learning to walk. The same action might not always lead to the same outcome because of subtle variations in the terrain or even just random slips.
So it's like trying to learn a dance move.
Yeah.
On a slippery floor.
Exactly.
The same steps might not always lead to the same result because of unpredictable factors.
That's a great way to put it.
Okay.
And this noise can make it hard for policy gradient methods to figure out which actions are truly responsible for success.
That makes sense. So how do we deal with this noise?
Okay.
How do we make sure the AI isn't thrown off course by these unpredictable elements?
Well, researchers have developed some clever techniques, like baseline subtraction and variance reduction.
Okay.
These methods act like noise-canceling headphones,
Okay.
helping the AI filter out distractions and focus on the true signal, the actions that consistently lead to better outcomes.
So it's like clearing the static from a radio signal.
Yeah.
Allowing the AI to hear the instructions more clearly.
Exactly.
Learn more effectively.
And just like with Q learning, we also have to address the balance between exploration and exploitation.
Okay.
In policy gradient methods, we need the AI to explore new strategies and adapt to changing circumstances, but also to exploit the strategies that have proven successful.
It's like trying to find the best route. Through rush hour traffic.
Yeah.
You might stick with your usual route most of the time. But occasionally you might try a new back road to see if it's faster.
That's a great analogy.
Okay.
And just like with navigating traffic, there's no one-size-fits-all solution. In reinforcement learning.
Okay.
We need to choose the right tools and strategies based on the specific problem we're trying to solve.
It sounds like there's a whole toolbox of techniques for tackling these challenges.
There is.
So we've got value-based methods like Q learning, which focus on figuring out the goodness of actions, and policy-based methods, which try to learn the best strategy directly.
Exactly.
It's like having different maps
Yes.
for navigating the same terrain.
That's a perfect way to think about it. And as we continue our deep dive into reinforcement learning, we'll discover even more fascinating algorithms and techniques that researchers have developed to push the boundaries of what's possible with AI.
I'm eager to learn more.
Me too.
Welcome back. We've covered so much ground.
Yeah, we have.
From the core elements of reinforcement learning to those inner workings of Q learning, and even those strategy-focused policy gradient methods. But there's one more frontier I'm really excited to explore: deep reinforcement learning.
Oh, yeah. It sounds like the ultimate fusion of AI superpowers.
It really does.
It is.
It combines the adaptive learning of reinforcement learning with the incredible power of deep neural networks, those complex structures that can find patterns in massive amounts of data.
Yeah, it's amazing.
There's neural networks that revolutionize things like image recognition.
Exactly.
But how do they fit into the world of reinforcement learning? It sounds almost too good to be true.
Well, think of it this way.
Yeah.
We're using these powerful neural networks to represent those crucial functions that our AI agents need to learn. Whether it's the value function that estimates the goodness of actions, or the policy that dictates the strategy.
So instead of those simpler representations we talked about earlier, we're bringing in these deep neural networks.
Exactly.
That can capture much more complex relationships between the agent's observations, actions, and the rewards it receives.
You got it. Remember that Atari game example we discussed where the AI had to learn to play from just pixels on a screen? With deep reinforcement learning, we can feed those raw pixels directly into a deep neural network.
Oh, wow.
And the AI can learn to play at a superhuman level.
Really?
It's like giving the AI a superpowered set of eyes that can see patterns and strategies.
That's amazing. But these deep neural networks can be incredibly complex, millions of interconnected nodes processing information.
It's true.
How do we even begin to train them within the framework of reinforcement learning?
Well, it's a challenge for sure, but we can leverage many of the techniques we've already discussed, like Q learning and policy gradient methods, with some clever adaptations. For instance, deep Q learning, or DQN, uses a deep neural network to approximate that all-important Q function.
So we're still trying to figure out how good each action is. But now we're using this incredibly powerful network to make sense of all the complexity.
You got it. But training these networks in the wild world of reinforcement learning presents some unique hurdles. The data we use to train the network isn't as neat and tidy as it is in supervised learning. The AI's own actions directly affect the data it collects, creating a sort of feedback loop.
It's like trying to learn a new dance move while watching yourself in a mirror. That distorts your movements slightly. You're trying to learn, but the feedback you're getting is constantly changing because of your own actions.
That's a great analogy to tackle this challenge. DQN employs a technique called experience replay.
Experience replay.
Imagine the AI keeping a detailed journal of its experiences, the situations it encountered, the actions it took, and the rewards it received. Then to train the network, it revisits those experiences, randomly sampling from this journal to ensure it's learning from a diverse set of situations.
So it's like learning from a variety of teachers instead of just one.
Exactly.
Giving the AI a more well-rounded understanding.
And that's just one of the clever tricks researchers have come up with to make deep reinforcement learning work. There's also this idea of using target networks, where instead of relying on just one network to do all the heavy lifting, we use two separate networks.
Two networks.
One to estimate the Q values, and another to provide the training targets.
Why the need for double the brain power?
It might seem counterintuitive, but this actually helps stabilize the learning process. Think of it this way. You're learning a new skill, and you have a coach guiding you. It's much easier to learn if your coach gives you consistent feedback rather than constantly changing their mind about what you're doing right or wrong.
So by using two networks, we're essentially giving the AI a more stable and reliable source of feedback. Allowing it to learn more effectively.
Precisely. And these are just a few of the techniques that make deep reinforcement learning so powerful.
It's a rapidly evolving field. with new breakthroughs happening all the time.
It's incredible to think about where this could lead. We've seen it conquer Atari games. But where else is it being applied?
Wow.
It feels like this technology has the potential to touch every aspect of our lives.
The applications are truly vast. Researchers are using deep reinforcement learning to develop robots that can perform delicate tasks.
Oh, wow.
Like assembling intricate objects or navigating through chaotic environments.
I've heard about AI systems that can write poetry or even compose music.
That's right.
It's mind-boggling to think about the creative possibilities.
Absolutely. And beyond those artistic applications, deep reinforcement learning is making waves in fields like healthcare and finance.
Oh, wow.
Imagine personalized medical treatments tailored to an individual's unique needs.
Oh, wow.
Or financial portfolios optimized based on real-time market conditions.
Yeah.
It's all within the realm of possibility. It's truly remarkable how this technology is blurring the lines between science fiction and reality.
It really is.
But as with any powerful tool, we need to be mindful of the potential downsides. It makes me think about the ethical considerations.
Absolutely.
Surrounding deep reinforcement learning.
That's an incredibly important point.
Yeah.
We need to carefully consider how these AI systems
Right.
will interact with humans, particularly in high-stakes situations like healthcare or transportation.
Yeah.
It's crucial to ensure they're aligned with our values and goals.
Right.
And don't unintentionally cause harm or perpetuate biases.
It's a reminder that we need to be thoughtful and responsible
Absolutely.
as we develop and deploy these increasingly intelligent machines.
Open and honest discussions about the potential impact of deep reinforcement learning are crucial. It's about ensuring this powerful technology is used for good and benefits all of humanity.
Well, on that note, we've reached the end of our deep dive into the world of reinforcement learning.
That's right.
We've explored the fundamental concepts, uncovered the cleverness of algorithms like Q-learning and policy gradient methods, and even ventured into the exciting frontier of deep reinforcement learning.
It's been a thrilling journey, and remember, this is just the beginning. Reinforcement learning is a rapidly evolving field with immense potential.
Thanks for joining us on the deep dive. Keep those minds curious.
Yes.
And never stop exploring.